Now, again, you were given a guided note sheet, so you may not need to write anything else down. But if you have anything that you want to write down as we go along, that's fine. Quite frankly, the first three names that I put up on the board, John Newland, Dmitry Mendeleev, and Henry Moseley, these are not names that we would ask that you memorize in any way, shape, or form. All I'm trying to do is talk to students early on about how the periodic table was put together. Part of that you've already seen, the SPDF orbital, why it has the shape that it does. Again, John Newland started off by organizing according to average atomic mass. However, if you paid attention to the periodic table, between tellurium and iodine, the mass actually decreases. So does cobalt and nickel. Dmitry Mendeleev based it on the trends of the periodic table that we're going to be talking about a little bit later in class. And Henry Moseley used the trends in the atomic number. Really, the two vocabulary terms that you should be aware of are on the bottom of this slide. So maybe that's where you want to circle those, or those are the two things in this first slide that are of importance. A period is referring to a horizontal row across the periodic table. A group is going down a vertical column. Now, I don't memorize this too much because, quite frankly, on the top of your periodic table, above the first column, it says group anyway. So you already know groups are the ones that go down, periods go across. But those are two vocabulary words that we will use when expressing where we are on the periodic table. And as you're going to learn today, especially with the E-Lab that we're going to do, we want to know what's happening on the periodic table as we go left to right, as we go top to bottom, with some of these behaviors of the atom. Now, the first group of the periodic table, the first family, is going to be the alkali metals. You know something is reactive, but it's not found alone in nature. Because if it's found alone in nature, it's not going to combine with anything. It's not going to interact with anything else. Alkali metals are very reactive. What I'm hoping to do at the end of the hour, if we have time, is I'm going to show you a demonstration of this. However, one thing to mention also about the alkali metals is they have one outer electron. Valence is a fancy term for an outer electron. I believe this is a term that was brought up last class. But valence is the same as an outer electron. Again, if we have time at the end of the hour, I'm going to show you that alkali metals are soft. When we think of metals, we think of things that are really hard and rigid, but not the alkali metals. To be a metal means you're a good conductor of heat and electricity. And then the last thing that it says, which is what the demonstration I'd like to do at the end of class, is that they can react with water. And if you think about that, water makes up the majority of our planet. Water makes up the majority of your body. If you have something that can violently react with water, it's pretty reactive. Now, when I say reactive for that third dash point, what I'm referring to is it can readily change. It can interact with other things. What we'll talk about today is how things react. Second column of the periodic table is the alkaline earth metals. They're also fairly reactive, so they're found as compounds in nature, but sometimes they're pure. They have two outer electrons because they're in the second column. So once again, they are less reactive than alkali, but still fairly reactive. The reason why we give some of these columns or groups of the periodic table a family name is because they all behave similar to one another. So alkali metals, excluding hydrogen, lithium, sodium, potassium, work their way down that first column. They all have similar behaviors. Alkaline earth metals, beryllium, magnesium, calcium, all have similar behaviors as you go down there. So that's why we refer to them as that. I'm going to now skip all the way across the periodic table for a little bit to the second to last column. The second to last column, starting with fluorine, is called the halogens. So again, this is the second to last column of the periodic table. They are non-metals. One of the things I had to tell you last class, in order for you to do all the lab, is there is a staircase on the periodic table. Everything to the left of that staircase is a metal. Everything to the right is a non-metal. What you're going to learn, probably starting today, but even more so next class period, is metals versus non-metals. How they behave is different from one another. How they get to an ion form is different from one another. And there's reasons why. Part of that is what we're going over today in class. They have 7 outer electrons. They react with metals to make a salt. And it's the only family of the periodic table that contains all 3 states of matter. Quick review of that. If an element is in red on your periodic table, that means it's a gas at normal conditions. If it's blue, that means it's a liquid. If it's black, that means it's a solid. So no other family of periodic table is that way. Most metals are going to be solid. Mercury is an exception to that. But the halogens are an important family that we're going to be going over more today. If you flip to the back side of your note sheet, the noble gases are the last column of the periodic table. And for the most part, they have 8 outer shell electrons, which means they completely fill their shell. If you think back to orbital notation with the up and down arrows, you completely fill your shell at a noble gas. I'm even wearing my noble gas t-shirt today, folks. I get science-specific clothing from my mother-in-law all the time. For the most part, they are not very reactive. So you won't find them combined with anything. Again, helium is an example of a noble gas. I do mention in the bottom here that there are some noble gases that could react a little bit if you force them to. I have just covered 4 columns of the periodic table. The lithium column, because again we're going to exclude hydrogen, is the alkali earth metals. The beryllium column is the alkaline earth metals. The fluorine column is the halogens. The helium column is the noble gases. Those are the only 4 what we call families because their entire column is similar. But you notice there's 3 more slides left to your note packet that I want to go over. The first is the transition metals. Remember the d orbital from orbital notation? That is your transition metals. It's the metals in the middle of the periodic table. What makes them unusual is they don't all have the same number of outer shell electrons. When I said the alkaline earth metals all have 2 outer electrons, again, we could write electron configurations to prove that, or you could look at the shorthand notation. Beryllium ends in a 2s2, magnesium ends in a 3s2, calcium ends in a 4s2. Middle of the periodic table doesn't do that. So they are metals, but they aren't all the same like the alkaline. They're also a lot less reactive. And when things aren't reactive, you can find them alone in nature. You can find pure gold, pure iron, pure copper. Like your house probably has pure copper in it. And the last 2 points I have down here is actually things that we will talk more about in the next unit when we talk about what makes a metal. So I'm not too concerned right now if you know this, but there are properties of things that make them more metallic than others. So in other words, I started off the notes by telling you 4 separate columns, that they all behave similar. We just grouped all of this middle section all together and say, that's just one big family, they're all pretty similar. That still leaves us a lot of the p orbital that we haven't discussed. The problem with the p orbital is some of them fall into a category that's called a metalloid. I mentioned staircase elements. Again, highlighted in blue is your staircase that separates the metals from the nonmetals. Things like boron, silicon, germanium, arsenic, antimony, tellurium, polonium. So everything above or below that staircase, excluding aluminum, they're considered metalloids. And what does that mean to be a metalloid? It means you're a little bit metal, a little bit non-metal. I would compare this to being similar to if you lived on the Wisconsin-Illinois border. There's a very good chance that you could be maybe a Bears fan because you're actually closer to Soldier Field than you are to Lambeau Field. So even if you live on the Wisconsin side of the border, you still have behaviors of, hey, I like this a little bit better. but then, hey, I like this a little bit better than too. So when you're on the border of anywhere, it could be a country, it could be a state, whatever, you're a little bit of both. And that's what those metalloids are, is they're just a little bit of both. That's also why we don't have a family that's a name for the nitrogen family. Because nitrogen is a non-metal. Phosphorus is a non-metal. Arsenic, oh, that's a metalloid. Antimony, metalloid. Bismuth, metal. This column does not have things that are common. Because of that staircase kind of separates out our metals from our non-metals. The very last slide. Our focus today is going to be on what's called the main group elements, which are the s and p orbitals. Because what you're going to find, the trends of the periodic table that we're about to go over, they apply more towards these main group elements than to the middle of the periodic table. When you get to those transition metals in the middle of the periodic table, so again, iron, cobalt, silver, osmium, whatever might be in the middle, they don't follow a nice, neat pattern. And because of that, we usually stick to the S and P elements instead. So again, continuing our notes on trends, to define the atomic radius, what's a simple way we can define the radius? We say the atomic radius, when we define it, what are we referring to with the radius? We're referring to its what? Something has a small radius versus a big radius. What are we talking about? Come on, ladies and gentlemen. We wrote this down in our lab. It shouldn't be tricky.
A distance.
That distance from... Yeah, no, again, radius is like half of a circle, remember? Something with a small atomic radius is a small atom. Something with a big atomic radius is a big atom. I put down an italics point here. What keeps the electrons around the nucleus? Well, what are the electrons attracted to? The protons. The nucleus has protons in it that attracts them. There are two things that are always going to determine these different trends. One is, how many shells do I have? So how many electrons do I have going out? One is, how many protons do I have in my nucleus? Now, my second bullet point says, as you go down a column, atomic radius does blank, because you're adding blank. Well, does the radius increase or decrease as you go down a column? You guys should have looked this one up. You should know this one. Atomic radius does what? Increase. I mean, you can just draw an arrow pointing up if you want to. Now, here is the tricky part. On your lab, you're either supposed to reference the number of protons or the number of shells of electrons. Think of rings in a Bohr diagram. Both of those numbers are increasing as you go down a group. Yet one plays a bigger role in the radius getting larger. So what do we think? Are the number of protons in the nucleus causing the atom to get larger? Or is the number of shells causing the atom to get larger? Kinsey says shells. Do we like that answer? Okay, so that's what my other blank would be. Third bullet point says as you go left to right across a row, which remember a row is just another name for the period. What happens in atomic radius as you go left to right? Does it increase or decrease?
Decrease.
It decreases. So we talked about this one at the end of last class. This is a little unusual. And again, the reason why, I even referenced nucleus in this one, so maybe you can fill in that blank on your own of it decreases because the nucleus, blah, 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 to pull on the electrons. So does it have more or less of something? On the very bottom of the page is a term that, again, we don't ask you to memorize. But what you need to keep in mind is this idea of opposite charges attracting. It's called Coulomb's law. Whether or not things are getting smaller or bigger, which is atomic radius, or easier or harder to gain or lose electrons, is all dealing with the attraction between the nucleus and the electrons. If there's a lot of attraction between the nucleus and the electrons, They can pull them in tight. They can hold on to them really well. If there isn't a lot of attraction, it's a loose holding. It's easy to let go. The second trend on here was ionization energy. Ionization energy was on your next page. Now, I'm not going to go through the full definition because that's what you're supposed to write down, but let's break it down this way. Atomic radius was about the size of the atom, big atoms versus small atoms. The next two trends are either about gaining electrons or losing electrons. Does ionization energy deal with gaining electrons or losing electrons? I misheard you. Is ionization energy about gaining electrons or losing electrons? Losing. So is it easy to lose or not to lose? Now the trend again as you go down a column, I'm going to ignore the blanks right now, but if you look at my second line, because it takes less energy to remove an outer electron due to whatever. Ionization energy is all about that loss of electron. If it's easy to lose an electron, it doesn't take much energy. It's kind of like the old phrase, stealing candy from a baby. It's easy to do because the babies don't have a hard, strong hold on that candy compared to what an adult would have. Low ionization energy means it's easy to lose an electron. High ionization energy means it takes a lot of energy to do that. So when you are doing that ionization energy page on your lab, what you want to be thinking about is two parts. One, is the value increasing or decreasing? So is it getting harder to take the electron away or easier? Secondly, notice the last couple of words I have on the slide, because the atom is getting smaller. In my mind, the trends in the periodic table all deal with the size of an atom. If an atom is small, its positive nucleus is closer to its outermost electrons. And if the positive nucleus is close to the outer electrons, they have a good strong hold on them. On the flip side, if it is a big atom, the electrons are far away from that nucleus. There's a lot of shells in between. That makes it hard to hold on. The last trend was electronegativity. And again, I don't need to fill the definition right now, but one of the things I put in parentheses underneath the definition, the bigger the number for electronegativity, the more pull it has. So if ionization energy is all about losing electrons, electronegativity is all about gaining electrons. I do remind you of what electron shielding is in this slide. Inner electrons reducing the pull of the nucleus on outer electrons. And the very last thing I put on this slide in parentheses is, in other words, the nucleus is closer to electrons to react with. If ionization energy is losing electrons, electronegativity is gaining electrons. Well, where do they gain them from? A neighboring atom. Is it easy to take an electron from a neighbor if you have a high electronegativity? Yeah, that's what that value represents. Think back to the size of the atom then. Are small things good at taking or big things good at taking? That's what you'd probably be referencing when it comes to electronegativity. So again, I have some blanks in here because I'm not just going to give you all the answers to your lab, but I'm hoping by talking you through this a little bit, it makes sense. There is one slide on here that isn't part of your lab itself. And what I say is reactivity is defined as an element either gaining or losing electrons. It's changing from its neutral form. Starting next class, you're going to learn why that's important. Here's what I'd like you to do to wrap up class. My second bullet point says, circle where the most reactive metal and nonmetals are. Metals typically lose electrons. So, losing electrons means ionization energy is the trend that we would focus on with metals. Metals want to be easy to lose electrons. If you're going to do something, hopefully it's easy to do. So right now, ladies and gentlemen, looking back at your lab or whatever it might be, what metal on the periodic table would lose electrons the easiest? What has the lowest ionization energy possible? Is it metals on the left-hand side or the right-hand side? Is it metals on the top or is it metals on the bottom? What do we think? Is it easier to lose electrons if you're small or if you're big? Let's start with that. Big. If you're big, your nucleus is far away from those outer electrons. So that means we need to go to the bottom row. What I want you to circle on this note page is the bottom left-hand element, francium. Francium is the most reactive metal on the periodic table because it is the biggest. Who was my group 18 people today? Did you have to do a lot of work for electronegativity for group 18? No. Noble gases do not gain electrons. There's no place to put them. Fluorine in the upper right-hand corner is the most reactive nonmetal. It has the highest electronegativity if you look back at those notes. The goal today is to show you these trends of the periodic table, because next class we can start talking about why is it important to be gaining and losing electrons. But elements just don't do that because they want to. Some elements are good at gaining, some elements are good at losing. That's what we wanted you to find out today.